Hello everyone, welcome to our physics lesson. Today we will be studying 2 and 3-dimensional motion. Before we examined one-dimensional motion, whether they were horizontal or vertical. We gave examples such as a coin falling from a Empire State Building or a student catching a bus, these types of questions. Although in our daily life, we may not always encounter with one-dimensional motion. Think about Ronaldo's greatest shots curving the ball like a pro, or think of Tesla's space shuttles. They go up to the space and flow in the space. These examples both have horizontal and vertical movements at the same time. To be more brief, while the object is rising vertically, it is also moving forward. So the motion happens in two dimensions. We can examine these movements in subcategories such as velocity and displacements and acceleration components one by one. So let's start with displacement and velocity vector. Okay. So let's draw x and y axis. X and y axis. Okay. And as we know, we call x axis as I, and for y it is j. Okay. And let this be our vector and has coordinates px, and the name of the vector, let it be r. A particle's displacement with regard to origin point gives us its position vector. And r is shown like this: x minus 0, because 0 is our origin point, I plus y minus 0, j. And this equals to xi plus yj. And r, the value of r, should be like this, in a root x squared plus y squared. So x is equal to, as we know, r times cosine theta. Theta is this angle. And y is equal to r times sine theta. And now let's draw another graph that shows the displacement vector. So this is again x and y, and this is I and j. So as we said, let's p is right here, x1 and y1, and let's say there is another vector, and that is r, and this is x2, y2. So let's suppose that point P moves to point R in time. Then the change in position vector becomes equal to displacement vector, which is this one. And let's call this delta R. Okay? And delta R is equal to R2 minus R1 vectors. And that is equal to x2 minus x1 I plus y2 minus y1 j, and this equals to delta xi plus delta yj. So V average is equal to delta r over delta t, and then V instant is equal to, we will use limit here, limit delta t goes to 0, delta r over delta t is equal to dr, we show it like this, it's derivatives, over dt. Okay, And if we draw same graph, x and y axis, with our velocity, we will get the formulas like this. So it's our x, y, and we have velocity vector just like this. And let this be vx, and this one y component, and this is theta. So this is our v. V vector is equal to vxi plus vyj is equal to v cosine theta I plus v sine theta j. And then v is equal to vx square plus vy square. And vx is equal to dx over dt. And vy is equal to dy over dt. And I would like to talk about, in one-dimensional motion, only a particle's speed changes. But in two-dimensional motions, a particle's both its speed and direction changes. And let's suppose that we have a curved road, okay? And a car is moving from point P1 to P2, and its change in velocity and acceleration will be shown as like this. Let's say this is our curved road, and let's say this is our car going like this, and this point right here shows it's, let's say, V1. The road let it this curving. So this point right here is P1, and then the car moves to here, and this point right here is like this, and V2. Okay, so again our V1 vector, and right here this is our, actually let's do it like this. Our V1 vector is like this, okay, and our V2 vector is like this, and the change is from here to here, and this is our delta V, meaning that V2 minus V1. So we have also average acceleration, that is A average is delta V over delta T, and this equals to V2 minus V1 over T2 minus T1. Now I would like to show you something. Our delta V vector, as you can see, its direction is like this, and also acceleration vector, they are in same direction. Average acceleration's direction is same with delta V vector. You can see, if you look at the motion, acceleration in a curved surface is always towards the center of the curvature. So acceleration is always towards the center of the curvature. Then our A instant would be like this. Limit delta t goes to 0. So delta V over dt is equal to just ijk components. Nothing is changing. Vx I over dt plus d vy over dt. Now j x y, and now z d vz vz dt, and right here is k. This is same as x y z. Now we can examine the change in acceleration. The component of this will give us information about particles change in speed and directional change for velocity. Again, we have a curved roller, let's say, and this is our particle, okay? And that's x and y axis, okay? And this is our vector A, and this is our vector A1, this is our vector A2. Okay, let's suppose that A is going to the center of the road, or the road is like just like this. Doesn't matter, try to guess that it's just going to the center. And this is the path followed by the particle, and A1 is the component of A which is perpendicular to the surface, and this exists in every situation. And for A2, this is a component of A which is parallel to the surface. A2 exists just in circular motion, okay? Now, after we finish this, now we can go to projectile motion, okay? Projectile motion. Projectile motion is, for instance, a rock throwing from a cliff or a bullet is thrown with an angle can be given as an example. Projectile motion has two components, x and y. A particle that is thrown moves in a constant speed with x direction. And in y direction, it makes a constant accelerated motion. And if we draw it with a graph showing its height and displacement, so our particle is moving upwards, just like this, and going then downwards because of the gravity, right? Oops. Now we have to draw it again, no problem. So as I was saying, it's going upwards, then downwards. Sorry for my drawing. And it's starting from here. It has velocity, the x component going horizontal and vertical for Vy. And it's again moving here. Again, it has Vx component and Vy. At this point right here, this is the maximum height. Okay, and at this point, its velocity Vy, y component of velocity, is becoming zero because it's not growing at all at that time. Just it has Vx component. And there is an also acceleration that is same with gravity. And right here, it again is now falling Vox and Voy, and just the velocity vector. A particle's velocity throughout x-axis doesn't change at all, and shown as Vox and Vo cosine theta. And particle's motion throughout y-axis is constant acceleration, and its velocity changes in time. And this is Vy, Voy minus gt is equal to Vo sine theta minus gt. And lastly, a particle's height at any given time is equal to displacement in constant acceleration motion. And this right here is equal to yt is equal to y0 plus Voy times t minus 1 over 2 gt squared. And we will continue to find equations like this in our next video. Thank you for listening. See you in next video.